I will talk instead of some instability, which shares some properties with dynamo action, but which is occurring in some electromagnetically driven flows. Okay, so it's a work which has been done with several people. So Paula Rodriguez-Imazio is a postdoc in our group. She's working on the numerical part. Sandeep Reddy, who is somewhere here, is also working on the numerical part of this problem. And Michael Pereira is a student who is working on the experimental side. And there is also François Petrelis and Stéphane, of course. Okay, so basically I will try to first present you some numerical simulation and some associated theory to this type of flows. And then I will try to finish with some new laboratory experiment that we are running right now. Okay, so when we talk in general about electromagnetic driving, people think about the classical case of a DC pump. When you have an homogeneous static magnetic field, you're also imposing with some electrodes an electrical current, and so you have your Lorentz force J cross B who drives a flow. This is, for instance, what's happening in the Zurich experiment, where they use currents to drive an azimuthal velocity field. Here today, I will talk about a rather different problem, but quite simple. So what happens when the electrical current is not imposed by some electrode, but induced by some time and space varying magnetic field? Okay, just like induction pump problem. And you will see that in this case, there is this problem is intrinsically related to some imaged instability, which occurs if Rm is large enough, basically. One motivation, or at least one system, who is based on this type of forcing, are the annular electromagnetic pumps. These things are used in some fast sodium breeder reactor for the cooling system. Okay, secondary cooling system, actually. So what is it? So you have an annular section here, which is confined between two concentric cylinders. There is in general liquid sodium, and to make the sodium circulate in order to cool down the part of the system, you have on the external cylinders some series of three-phase electrical coils and some ferromagnetic parts I will not describe here. The main idea, it's what I try to draw here, the main idea is that using these coils, you generate a very strong radial magnetic field inside the gap. Then by playing with the polarity of the coils, this radial field will have some sinusoidal dependence in Z, and it will propagate in the Z direction. Okay, so you have some electromagnetic wave, radial wave, which is propagating in the Z direction, so you have a forcing in this direction. And so the interesting point here is that there is some indication that this system may be unstable if Rm is large enough. So that's a problem for cooling down, nuclear reactor, obviously. Okay, so first I will start with the simulation. So we try to find a very simple setup, trying to reproduce the minimal ingredients in an electromagnetic pump like that. So we are solving full MHD equation in a cylindrical geometry. So you have two concentric cylinders. We're using the code Heracles, which is a finite volume MHD code. So here is the gap where the conducting fluid is. To model these electrical coils, we are imposing a surface current at the external boundaries, okay? So we can choose it analytically, so we choose a very simple form. So we have a current which is like sine Kz minus omega t, okay? So it's propagating in the Z direction. And the cylinder is infinite in the Z direction. Okay, when you do that, you have a magnetic Reynolds number controlling the problem, of course, which is based on the velocity of the wave, of the electromagnetic wave. You have an Hartmann number. You can also define a kinetic Reynolds number, or what is equivalent to the magnetic Prandtl number. And in everything I will show, the velocity is always normalized by the velocity of the electromagnetic wave. Okay? So this is one typical result of the simulation. So here it's 2D simulation. I will go back to 3D runs later. First, I want to focus on very simple 2D simulation. So this is a cut in the RZ plane. It's a color plot of the velocity field and the magnetic field. So the inner cylinder is here, the outer cylinder is there. You can see that we are imposing the current on the outer cylinder since the field the magnetic field is stronger here. And if you look at, so you have to imagine this structure propagating in the z direction. And in the simulation, you obtain this for low magnetic Reynolds number. You obtain this kind of flow. So first, you can see it's quite homogeneous, okay, in air, except in the boundary for the boundary condition. The value, if you look at here, is close to 1. So it means that for this value, the velocity, the fluid, is pumped nearly in synchronism with the electromagnetic wave driving the motion. Very efficient state. Okay, so this is, for example, a profile. It's some kind of Hartmann-like profile. Okay, very squared profile.
And what are the colors in this segment?
So here you mean?
Yes.
Like here. So here it's for.
I mean the second down, middle one. No.
This one. So this is the color shows the amplitude of the radial magnetic field. Okay. So just to show you that you have field lines propagating quite radially. Not completely, but quite radially. Okay, what happens when we increase the RM from these states? So what we get can be summarized on this curve here. So it's the normalized flow rate inside the domain as a function of the magnetic Reynolds number for different value of the Hartmann. At small Hartmann, you get the black curve, which means that an increase of the magnetic Reynolds number will make the system smoothly bifurcate, or you have a smooth transition, let's say, from a synchronous solution to a smaller and smaller flow rates until you get very small values. Now, when you do the same thing at higher Hartmann number, for example, 500, the blue curve, it's very different. An increase of RM first changes nothing, okay? The flow wants to stay in this strongly magnetized regime where it's flowing in synchronism with the wave until you reach a critical value of RM for which you have a very strong bifurcation, very sharp, when then you go to some stalled regime, okay? The flow suddenly starts to flow with a very, very small flow rate. So this is what we call the stalling instability. Okay, it shares some analogy with the stalling of an asynchronous motor, as I will show you. So if you zoom on this part here, just to have a better idea of what's going on, you get this curve. So in fact, this bifurcation is associated to some B-stability. So we start from here, as I said, we increase RM, we get the black point here, which are synchronous solutions, until we fall down for this critical value of RM to very low flow rate. And on this branch, we can go back with RM and we keep here a small value, so very strong hysteresis. And in particular, there is a bistability between this branch and this one. What is quite interesting is that this bistability involves two states very different. On the upper branch, you have the Hartmann-like profile I talked about. But when you jump to the lower branch, now you're more like creating some kind of annular Poiseuille flow. Okay, so it's a bistability between very different regimes. Okay, so how can we understand that? There is a simple way to capture the essential physics here. I will not go through all the model, all the detail of the model. I will just try to summarize what we're doing here. So to have a nice expression of the force acting on the system, we are supposing that the velocity will be constant. Okay, we are supposing no dependence in the radial direction. It's just like a solid block velocity. Okay, we suppose that. There is some other assumption, small gap, the fact that the fields are going to be purely traveling wave. If you do that and you inject this in the induction equation, you can obtain a very nice expression for the force acting on the fluid as a function of the velocity of this fluid, okay, which is this expression. So again, you have some magnetic Reynolds number, some Hartmann number, which control this problem. Okay, again, the velocity is normalized by the wave speed. And this is your expression. So the first part is the Lorentz force acting on the fluid, while the second part is the viscous dissipation. Okay, I just chose here to use a quadratic dissipation. Okay, so just to have an insight of what is it, I just draw this force. So the black curve here is the Lorentz force, while the red one is the viscous dissipation, turbulent dissipation or whatever. The fluid is operating at the intersection between the two forces. Here we have a stable point, for example, for this set of parameters. And you can see that this is operating very close to synchronism with the wave, close to V equal 1. Now, as you increase the magnetic Reynolds number, basically the black curve is going down. And what you see here is that there is now more intersection between the two curves. You have a new stable solution to very small values, some unstable solution here, and your synchronous stable solution. As you increase RM, you can see what's happening. In fact, it's a little bit more like François talked this morning. The unstable and the stable solution will get closer to each other here until they reach a saddle node bifurcation here, where these two solutions disappear. When you reach these points, the two solutions disappear, and the system has no choice than going to the remaining stable point of the system, which corresponds to a very small velocity. Okay? So, yeah. I could go through all the derivation, but then I will be done with my talk. So, but we can discuss after if you want. It's quite simple, in fact. Huh? Okay, so again, I won't show you all the comparison between this simple model and the simulation. It's quite a good agreement. Just to illustrate, I showed you, so this is my parameter space, Hartmann RM. It's a color plot of the flow rate. So what is important is to note the transition between synchronism and stalled flow, okay? And this is for the simulation. So in both cases, the transition is compatible with some very nice scaling. The critical Hartmann is scaling like the square root of the magnetic Reynolds number. Again, I have to say, here these are laminar simulation, okay? Very low Reynolds number. So before I switch to turbulent one, I just want to say one word about the physical mechanism. Okay, so again, I plot it against the Lorentz force. And this instability, it's interesting because, in fact, it's based on magnetic flux expulsion. When you reach these points, what happens is that imagine you have a small perturbation where the velocity decreases. So you increase the slip between the velocity and the wave. By doing that, the magnetic field lines are sheared. And as a consequence, you have flux expulsion from the bulk towards the boundaries. When this happens, the Lorentz force inside the bulk flow decreases because you have less magnetic field. So the flow is less accelerated, so you amplify your decrease of the velocity field. So you have a runaway situation like that, where when you reach this point, a decrease of the velocity creates more flux expulsion, which amplifies the decrease, so your system rapidly escapes on this branch until some other dissipative mechanism come into play, which is here the viscous dissipation and its associated quasi-like profile. Okay, so this is, again, color plot of the magnetic field and the velocity field after the transition. So you can see that the energy is localized close to the boundary now. I don't know if you see it very much, but the field lines are also strongly tilted due to the velocity field. And the velocity field satisfies some nice quasi-like flow. So this is the physical explanation. Since it's flux expulsion, you can introduce some kind of magnetic Mach number, which is the ratio between the velocity of the fluid and the Alven speed. If you do that, if you introduce this Mach number or scaling for the apparition of the instability, translate it to some Mach number bigger than a number, which depends on the Reynolds number. And it's a nice prediction for the occurrence of instability. But on the other hand, you see that when Reynolds number become large enough, you expect a very strong constraint on the instability threshold. So that's why now we want to switch to turbulence simulations. Okay. So Paula has done some simulation where, so basically it's quite similar to before, except that we wanted something more realistic. So we increased the Reynolds number. So now the Reynolds number is between 5,000 and 10,000, which is the maximum we can more or less achieve with a numerical simulation. And in addition, the surface current now has a restricted size. Okay, so it's just to simulate the fact that any pumps will have a finite size. Okay, so we're still simulating all this regime, but the active region, the magnetized regime, is only now has only a finite size, and everything is the same. Okay, we have the same current, same numbers. Okay. So this is, for example, what we observe at low magnetic Reynolds number for Reynolds number now 6,000. Quite similar to what you've seen for the laminar simulation. Okay, we have synchronous flow, very homogeneous, except here where we have the inlet-outlet effects of the finite size of the pump. And the profiles are still very close to an Hartmann profile. But when we increase the IRM for this turbulent simulation, we get this instead. You see now it's very different. It's quite surprising. Inside the active region, what happens is that you get some region here close to the electrical coils, close to the surface current, where the flow is still flowing in synchronism with the wave. Whereas close to the inner cylinder, you have now a strongly negative velocity field. So the flow here is pumped backward to the driving wave. It's quite clear here on the profile. You have this synchronism region and then here this negative region. Very different from what we obtain in the stalled regime for the laminar simulation. So does it mean that the theory is completely wrong, the one we derived for the laminar simulation? Not completely. So one way to understand what's going on is to arbitrarily divide the domain between two parts, okay, what I will call the pump 2 and the pump 1, related to the inner part to the outer part of the pump. If you do that, you can plot the normalized flow rate of each region as a function of the metric Reynolds number. And what appears is that pump 1, the region close to the 1, just behaves like it doesn't want to stall. It stays in synchronism. On the contrary, the other region here will stall, following the same kind of mechanism that what we see in the global laminar simulation. Physically, it can be summarized on this curve. So here, to get this curve, what I do is I take my pump in a turbulent regime, we impose a flow rate, and we measure the Lorentz force and the flow rate in each individual region. If you do that, you get these dots, so the color obviously correspond to the two different regions. And what is surprising is that all these dots collapse on the same curve, which is the theory that I described before. So what does it mean? It means that we have a single system, but each region of the fluid, when the flow is turbulent enough, is operating on different functioning points of its force flow rate characteristic. Okay? So another way to say that is to say that when we become turbulent enough, the flux expulsion is acting only locally. So you can have region of space when you have strong flux expulsion. And so this can lead to this strong negative velocity and these strong large-scale vortices in the gap. Okay? Okay, and of course it's interesting because once you now switch to non-axisymmetric simulations, you have this kind of configuration where the inner part is flowing in one way, the outer part is flowing the other way. There is a strong shear, so it's strongly unstable to non-axisymmetric perturbation, probably to some Kelvin-Helmholtz instability. Well, we're still investigating this regime. But the point is that once this instability occurs, the flow becomes fully non-turbulent, fully non-axisymmetric, fully turbulent, fully fluctuating. And so the efficiency of this system is very low. Okay, the flow rate which is developed by this system is very far from synchronism. So that may be this kind of scenario which occurs in these giant electromagnetic pumps which have been used in industry, where they see some strong drop of the flow rates or at least some low frequency pulsation that may be related to that. Okay, so we still need to continue that and to understand better what's going on and how to suppress this instability. And so now I would like to switch to experiments. I don't know how much time I have left. Okay. Okay, good. So I can take a break. Yeah, so you saw, so we have a well-defined theory for laminar flows. When we switch to turbulence simulation, things become more complicated. We have this local flux expulsion, which is already quite hard to relate to theory. So the question is, of course, what happens when we go to very high Reynolds number? So that's where experiments are useful. So we have built a very simple experimental setup in order to see this instability. So this is only a small version of a future experiment. So this is a picture of the experiment. So what happened is that we have this upper piece here, which is an annular channel, which is filled with liquid gas instants. Okay, it's this size. It's a small experiment. It's this size. It's filled with liquid gas instants, and we want to drive a motion, well, obviously in the azimuthal direction. To do that, we could use some combination of coils and electrical currents like we do in the simulation. Instead, we choose a more simple way to do it. We take this disk, so it's a disk on which we have fixed 16 magnets with alternated polarities. Okay, by alternating the polarities, we are creating some vertical magnetic field, which is sinusoidal in the phi direction. So when we put this disk just below the annular channel, and we rotate this disk, you have some electromagnetic wave, which is like cosine m phi minus omega t, which is trying to drive the flow in the azimuthal direction. So that's the idea. So to measure the flow, we're using ultrasound Doppler measurements. We also have some potential probes. We tried pressure sensor, not very successfully. But well, these two guys are enough to characterize the flow. All right. So these are some preliminary results. So this is the velocity measured by both the potential probes and the Doppler measurements. So there is agreement between the two measurements as a function of the disk frequency. So clearly there is a driving of the flow, very strong, in the azimuthal direction. We were not able to measure any velocity in the other direction, so it's really a strongly azimuthal velocity field. It seems to result from an equilibrium between the Lorentz force and the viscous dissipation, since the nice model I described just before fits very well these experimental data. Okay? Now, if we divide the velocity by the wave speed, we get this curve instead. It's another way to look at this. But it's also more useful to understand what's going on. So by increasing the disk frequency, or by increasing the magnetic Reynolds number, which is the same thing, we observe a smooth transition, just like in the simulation, from a synchronous solution to a smaller and smaller flow rates. So this is really like what we see in the simulation and the theory. On the other hand, I have to say the transition is smooth. Okay? So we are still very far from this very sharp bifurcation that we are expecting, which is really related to the flux expulsion. Okay, so clearly the numbers here are still too small to observe this instability. But still, there is some interesting results with these small-scale experiments. So we were looking for some unstable regimes. One way to see that is to add another disk on the top of the experiment. So now the liquid metal is trapped, sandwiched between two rotating electromagnetic waves. Okay, so we are spinning the disk in counter-rotation. So you could regard this problem as an electromagnetically driven von Karman flow, okay? Which is quite interesting because then it's non-intrusive, so we can see how the flow behaves. But here, just continue to look at this problem as the pump problem. We have a pump, and now we are imposing some constraint with the other wave, okay? We have two electromagnetic waves trying to drive a motion, which should cancel each other in the midplane. And if you believe the theory, you should have no motion in the midplane, for example. But what happened is that? So this is the velocity in the midplane measured by the Doppler probes as a function of the time. And what you can see is very different from zero velocity field. Huh? Actually, what happened is that we have chaotic reversals between the two symmetrical states, where for a given time, the flow prefers to follow one of the disk, one of the wave, then suddenly stop and follow the other. So we have this kind of very unstable regimes. If you think of this problem like the other disk is a charge, is an external load that you're applying on your pump, you can see this problem as the pump is functioning well, close to synchronism, but then it switches, okay, due to the load, then it comes back. So there is this kind of interesting dynamics. Okay, the distribution is by bimodal. And so this is clearly not predicted by the theory. So clearly, when we go to high Reynolds number, this kind of system can become unstable, okay? So that's what we are trying to understand better now.
So
Yes.
One is synchronization with one disk, bottom one is synchronization with another disk. Yes. Oscillating between the two.
Sorry?
The above positive.
Yeah, one disk is positive, the other is negative.
So they switch it between the two.
Yeah, so actually here you're following the top disk, here you're following the bottom disk, and so on.
They're rotating at the same speed.
And they are both changing at the same speed. If you start to explore the speed, what you see is that you're changing the density, the PDF of the system. Okay, it's because, well, that's what we're observing right now. If you change the speed, you're changing this. You go from, it's very, very close actually. For a very, very small difference, you will go back to the flow following only one of the wave. Very small difference. Okay, so just to conclude. So from the numerical simulation, we are studying this stalling instability, which seems to be due to flux expulsion. I think it seems to be very interesting, at least for two things. First, it's an instability which is strongly related to flux expulsion and induction. So there is a lot of things to understand about the mechanism, especially in the turbulent regime. But it's also interesting from the industrial point of view, because then you can find a way to suppress this instability, which is, of course, a big stake for cooling down, fast breeder reactor. Okay, and for the laboratory experiments, we see this transition, but it's still very smooth, so there is no way that we can, for now, relate what we see here in the experiment to the flux expulsion instability that we are really observing in the simulation. But still, we observe some unstable regimes. So the perspective now is to better understand what's going on in the simulation, especially in the 3D simulations, and trying to build a bigger experiment to see this flux expulsion instability. It's a complicated task. It's something similar to the dynamo problem. The magnetic Reynolds number which are involved are large or huge. So basically, you need to switch to sodium, clearly, and to build very big experiments. But we'll try it. There are several ways to play around. You can use a pressure gradient to accelerate the flow or decelerate it. It should help to see this flux expulsion. So that's one perspective of this work. Thank you.
What is actually the expected RM in the big pumps of the SFR, and what is the RM in the Pendulum, the small pendulum experiment?
Oh, sorry, I didn't.
What is really the RM in the big SFR pumps, and what is the RM in the pendulum experiment?
So, in the big industrial, the biggest experimental pump which have been built, which is more based on this, this configuration here, the RM of order of hundreds, it's very big, it's very big stuff. So, the smaller one, which are used for secondary cooling system, it's around 20. And around 20, they already see this weird low frequency pulsation in the flow. Now, in the small scale experiment, I mean, I don't want to tell you the RM, but of course it's very small. It's like of order 1, even, well, yeah, order 1.
Just in the industrial application, the use of an annulus rather than a full pipe, is this motivated by keeping RM small in the gap? Or?
No. It's a good question. So I think there is one technical reason. There are several technical reasons. But one technical reason is that you want an inner part which is made of ferromagnetic cores to canalize the thin lines to force them to be really radial inside the gap. If you remove that, I guess it's going to be more complicated to keep the field radial. So you really want, because you really want the thin lines to do some loops, to cross the gap, comes back, and so that's